Okay, hello, all those who, well, I guess it's optional Tuesday, isn't it? Optional Tuesday, so all of you, enjoy your optional day. Um, Today we want to talk about differentials. The application of differentials is almost the same as the application of linear, uh, linear approximations, okay? So here's what we're talking about. If we were to take a curve and we were to consider a line tangent to the curve, there are some important aspects to that curve. First of all, we're going to focus on dy over dx, which we have referred to as the derivative, correct? And we would say that that's really the same as f prime of x. So a differential is simply this. We multiply both sides by dx, we get dy is equal to f prime of x dx. F prime of x dx. Now, graphically, we want to understand what this means. I can have a coordinate here called x, and I want to look at the change. So dx, dy means a change in x over the change in y, or change in y over the change in x. As I move to the side, okay, there is a certain change in x for the function. We call that delta x. Delta is a capital, or that's a capital letter for D in Greek, okay? There's also a delta y, and that represents the change in the y value. So everybody okay with that? Now, I want you to know that delta y over delta x is not the same as dy over dx. But in close proximity, they become almost the same. So what is dy over dx? Well, we say that delta x is the same as dx. But this portion here is dy. This is the drawing you want to keep in mind. Dy goes up to the line, whereas delta y goes to the original function. See the difference? The dy and dx, those refer to the derivative, which is the tangent line, whereas delta x and delta y refer to the original graph. Okay? Now, you can see that in this situation, which is greater, delta y or dy? Delta y. And as we move further to the right, would you agree that delta y and dy get farther and farther apart? However, if we were to look at delta y and dy within a smaller proximity, they would be a lot closer to each other, wouldn't they? So why would the differential of a function be useful? Dy equals f prime of x dx helps us estimate delta y in close proximity. So you remember that yesterday we did a, what was our topic yesterday? Linear approximation. Linear approximation and differentials really have the same type of application. They allow us to approximate within small intervals. So let's try the basic piece, and we'll try just a little bit more difficult. It says find the differential dy, and then B, evaluate the value dy for the given values of x and dx. So your worksheet that you got yesterday, half of it was what we did yesterday, and the other half is what we do today. So you don't receive anything new today. You just continue on with that, okay? So find the differential. dy is equal to f prime of x dx. So I need the derivative of f of x. What's the derivative of 3x? What's the derivative of negative 1 over x? Very good. Plus 1 over x squared. Everybody okay with that? Negative x to the negative 1. Drop the negative 1 in front, subtract 1, positive 1 over x squared. All good? So that's the derivative. That's f prime of x, and we attach a dx. So we're going to estimate delta y. We're going to estimate the change in the function given the change in x. Okay? So dy is equal to, if x is 2, I plug in 2 for x, so 3 plus 1 over 4 times 0.5, or 1/2. Or dy is equal to 3 plus a fourth, 13 over 4, times 1/2 is 13 over 8. So let's understand what the heck that means. As we look back at this picture, we estimated that this increase, delta y, is 13 over 8. Was it actually 13 over 8? No, that's what that's what dy was. But it gave us an approximation, okay? How far off are we? We don't really know. We could compute that, and we'll do that in a later problem, but we're just estimating that, okay? So the 13 over 8 is actually the small one, but it estimates the big one, okay? We're using it to estimate the big one. Okay, let's try another one. Y is equal to 3 over x plus 1. X is 1, and dx is 0.01 or 1/100th. So I have dy is equal to f prime of x dx. Anybody want to tell me how to take the derivative of 3 over x plus 1? I like the chain rule. It's one of my favorites. 3 times x plus 1 to the negative 1 power. What's the derivative of the inside? 1. And then the derivative of the outside, we drop the negative 1 down. We get negative 3. It'll be over x plus 1 quantity squared. Everybody convinced by that derivative? So I have dy is equal to negative 3 over x plus 1 quantity squared times dx. What do I do now? Yep, just plug in your x value, which is 1. So I get negative 3 over 1 plus 1 is 2, squared is 4, times 1 over 100, get negative 3 over 400. Yeah, I really like it if you express it in a rational form. That's the first type of problem you're going to do in your assignment today. Could you handle that? Okay, let's look at the second type of problem you're going to look at. It says compute delta y and dy for the given values of x and dx equals delta x. Then sketch the diagram showing the line segments with the lengths dx, dy, and delta y. Sounds super confusing. It's going to make a lot more sense when we draw the picture. Okay? Let's draw a graph. What does x cubed plus 1 look like? Yep, up one squiggly. I like the way you think. There we go. So I'm going to draw a rather kind of a misshaped graph because it's hard to draw these things in really close proximity. But, is everybody okay with that? Okay. So what is the x value that I'm using? I'm using 1. So I'm going to draw a tangent line at 1. Can somebody tell me what f of 1 is? If I plug in 1, what's the output? 2. Is everybody okay? Now, we've done this, okay? It says that I'm going to have a certain change in x. So I'm going to move to the right a certain amount. What's my change? 0.2. So I'll be over to 1.2. Now I know this doesn't match up in terms of scale, but I'm drawing it to help us so that we can understand and see it better. So I'm going to put 1.2 over here. So that means that this dx, which is the same thing as delta x, is equal to 0.2. That's how far I'm going to the right. Okay. And from there, I go up a certain amount. And I'm going to have 2 squiggles. One of the squiggles is delta y, and one is dy. Is the green delta y or dy? Delta y. Delta y refers to the actual change in the function, whereas dy refers to the change in the rate. We draw it to the line tangent. Is everybody okay with the pictures that I drew? Okay. So we're almost ready. There's just one last thing that I would like to do with you. If you plug in 1.2, could I determine the output at that spot? Yeah, let's figure out the output at that spot. We'll take our calculator. We'll take 1.2 and cube it. Isn't that great? Logan didn't even have class this morning. He got up nice and early to come on in. It wasn't for Corral, it's for math. He wants to learn math. Right, Logan? He's not even listening to me. 2.728. Are we okay with that? Everybody good? No concerns? Awesome. Then it says compute delta y and dy. Delta y is equal to, it's staring you right in the face. If it was a snake, it would bite you. 2.728 minus 2 is 0.728. So is dy going to be greater than that or less than that? How do you know? Because you can see from the picture, right? It's not always going to be less. It's just in this situation because of the picture, you could tell it's going to be less. Nope. The next one we look at should be different. I think I included one like that. Right, if the tangent line was above, that would be different, right? But the tangent line is below. Okay, it also says to compute dy. Well, dy is equal to f prime of x dx. So dy is equal to, what's f prime of x? 3x squared times dx. What do I plug in for x? For x, I'm going to plug in 1 because that is where you draw your tangent line. So I get 3 times, what is dx? 0.2. That's the change. It's the same as delta x. And I get 0.6. Are those close? Yeah. Is the dy less than the delta y? Yep. Does it confirm your drawing? Does it make sense with what we put on the board? Good. No big deal. All right, we flip it over. Let's do the same thing. We just have these couple pieces to finish off with. We're going to do the same thing, but we have the square root of x minus 2, x equals 6, and delta x equals 0.1. So what does the graph of square root of x minus 2 look like? Yeah. Something like that. Is that okay for y'all? Okay, what's the x value I'm using? 3, 4, 5, 6. What is the output at 6? 2. How'd you get that? Plugged it in. What should I draw now? Tangent line. How far should we go over? 0.1. Watch how I draw over 0.1. You're going to love this. Where does that bring me to? 6.1. And then I'm going to go up. And I'm going to have 2 squiggles. I have a green one. And I'm going to have a blue one. One of these is delta y and one is dy. Which one is delta y, the blue or the green? The green. Delta y goes to the function. Delta y goes to the function. Dy goes to the tangent line. So is dy going to be an over approximation or an under approximation? Over, right? Because you can see that dy is above the delta y. The tangent line sits above the graph. So Rowan asked about that earlier. We have that situation playing out right in front of us. Yeah, you can see that dy sits above the curve. It's bigger than delta y. See how the tangent line is above the curve? Last time it was below. Yeah. It would be just the way you draw it. I don't think I could draw the tangent line below the curve without going through in more than one spot. You know what I mean? Like if I drew it like that, it would be below, but that's not tangent anymore. Tangent line needs to represent a linear approximation at that spot. Excellent point. Okay, so look at Rowan's point. She's saying if you draw this tangent line here, it's gonna whoop. If you draw this tangent line here, it's gonna end up crossing over there. We are referring to the immediate region. Okay, yeah, that immediate region. Dy always goes to the tangent line. Delta y goes to the function or the curve. Okay. All right, I want to come up with one more y value. If this is 6.1, what is that value up there? What is the square root of 4.1, somebody? Okay, can somebody then tell me what is delta y? .025. Looks like I drew it in the wrong spot, didn't I? Should draw it from here. 2.025. 2.025 minus 2 is 0.025, which is delta y. So yes, you were right, Alex. It is 0.025. Zane, you were right that I did not draw it to the correct spot. So should we end up with dy bigger than 0.025 or smaller than 0.025? Bigger. So what we need to do is we have dy is going to be equal to f prime of x dx. I need the derivative of the square root of x minus 2. How do I find that derivative? Chain rule. So I have u to the 1/2. I have x minus 2. What is the derivative of x minus 2? 1. What's the derivative of u to the 1/2? So I get dy is equal to 1 over 2 roots of x minus 2 times dx. What is it that I plug in for x? 6. 6 minus 2, square root of 4 times 2. So dy is equal to 1/4 times what? 0.1. And I get 1 over 40. What is 1 over 40? One divided by 40, and I get 0.025. So would you say that that's a close approximation? Yeah, I'm guessing Katie rounded up to get 0.025 for this one. Yeah. Now we took the square root of 6.1 or 4.1, excuse me. You can see that 2.0248. So excellent. Good work. Yes. I will let you know when we get to the test, regarding the decimal or the fraction. But in this situation, without a doubt, I prefer to try to express as a fraction as much as possible with some of these. But we were rounding these off all the time, weren't we? So when you start rounding them, that's a sign to go right to a decimal. But I will tell you explicitly on the test. So like this one right here, I would say leave your answer as a rational number, and we'll see. Square root of 80 or 64.3. We're going to use differentials to do this. So picture yourself, Isaac Newton, sitting back in the year 1600, and you're trying to find out the square root of 64.3. And you look at a friend, you say, what's the 64.3? And your friend says, well, it's about 8, right? It's about 8, right? He's like, I don't want about 8. I want an exact value. I want a pretty good value, okay? I want, something that's a lot more accurate. I'm like, well, okay. All right, well, let's figure out something. What's that? Well, because the square root of 64.3 is not the square root of 64, is it? To be able to do computations. So he's doing computations. He's designing things. He's trying to prove that the Earth is not the center of our solar system, but rather the sun is, right? All right, so we set this up. Sorry, I forgot to record. Actually, I knew I didn't record. I just didn't want to get the problem wrong. But let's see. Let's see what happens now if we take this whole 3 divided by 160. Is that equal to the square root of 64.3? Let's check. Second square root of 64.3, and I get no. Exactly. This is dy. It's what we add on to this. Right? We know the square root of 64 is 8. This is then the change in y. So we should have about 8 and 3 over 160. That should be the result. That's an approximation for the square root of 64.3. Okay? So let's try that. 8 plus 3 divided by 160. And let's see how close those are. What do you think? I would say that they are very close. Very close. That's the change. That's what you, that's dy. We won't do the bottom one, but let's do this next one, okay? 3.01 to the fourth. Yes. 8 and 3 over 160. Anybody want to guess what the x value is? 3. Anybody want to guess what the delta x value is? 0.01. Anybody want to guess what the function is? X to the fourth. So we're going to use differentials to approximate 3.01 to the fourth power. Now, I totally understand that you could take 3.01 and multiply it out 4 times. But I could also put a 10 on this and see how you feel about that, right? So let's give this a shot. F prime of, or I'm sorry, dy is equal to f prime of x dx. Yes. Yep. Dx and delta x are the same things. Okay. All right. What is f prime of x? 4x cubed multiplied by dx. What do I plug in for x? 3. What is 3 to the third? 27. 27 times 4? 108 times 0.01. So that will be 1.08. My guess is if I take 3.01 to the fourth power, I don't get 1.08. What is 3 to the fourth power? 81. So then 3 to the, or 3.01 to the fourth power, we would say would be 81 plus 1.08, or approximately 82.08. Let's see what we get. Because so this is the idea. See how the x value increased by 0.01? The question is, what should the y value increase? And we've determined that the y value should increase about 1.08. So we take this y value, 81, and we increase it by 1.08. I take 3.01 and I raise it to the fourth power, and I get, is that about 82.08? It's pretty close. So again, the approximation is there. Okay? 82.08. Scratch off that one. You guys have all the homework you need? Finish that worksheet. Tomorrow you have a work day in class. Thursday you have a work day in class. When's your homework due? Friday, because